Recording in progress.
Do you have any question from what we did yesterday? Do you remember what we did yesterday? So we have been, I'm trying to teach this introductory astronomy in terms of how are you measuring basic quantities. You are focusing mainly on distances. Any comment? So focusing mainly on distances. So we started with how distance to different planets are measured. We use two things. One is that laser to take the Doppler then you use Kepler's law on top of that to get the distances of different planets with respect to Sun. In particular, our Sun, we use it as a tool to make measurement at two extreme points, looking at stars in the sky, and use parallax method to calculate angles. That angles can then be used to calculate distances. So first we started with laser plus Kepler's law. Then you use trigonometry, and that's the way you get these things. From then on, to measure anything else, we are going to rely on some physics, which is completely related to what happens in these objects. And I explained to you that stellar evolution is very interesting thing because stars can be in a stable place for a long time during the stellar evolution, just in particular when hydrogen burning is going on. And we understood why it takes long time also, because we want to create neutrons which are not already present when you take the hydrogen atom from this. Then I introduced the concept of secret variables, and we said like why there is a pulsating, and we understood that the pulsating has to be related to the property of the star itself, because the whole thing is triggered by the fact that the star can absorb photons, thereby they get momentum from all the absorbed photons. But the problem is, if the momentum itself try to push it outside, if the star has sufficient mass, nothing will happen. So you have to be in a star which is at the edge of the equilibrium. Means if you don't do anything, there is a nice balance between gravity and whatever is the outward pressure. But if you introduce additional pressure, which is coming from momentum of photons, then this envelope will expand. So this is the thing we said. So there is a well-defined physics which is governed by again fundamental physics of what is the absorption cross section and how elements at different temperature, whether they will hold all the electrons together or they will become ions. So there are 2-3 concepts you have to remember, because of which you are in a situation where you can think of there is a finite kind of minimum and maximum radius between which a star can oscillate. And what is being found observationally is that more luminous objects oscillate with a higher frequency compared to less luminous object. That means if you know the frequency of oscillations, you will be able to measure, you will be able to guess what is the luminosity. If you know the flux, you can actually calculate. This is the thing we said. So then we also understood we can. So this is where we were, and then I introduced basically 2 other things I introduced. One is related to the whatever you call main sequence turnaround, where the stars are turning around when the hydrogen burning finishes and helium burning happens. Again, I explained to you, probably you already had a lecture on this yesterday, hopefully. So we can also use, that means this kind of main sequence is more or less common to all star clusters. So if you know different star clusters by matching where the main sequence are, you can find the distances to the star clusters. So now that we have done these ones, we said like now we have a ladder of measurements, we can keep on doing it. So if you have specific variables whose periods are known and luminosities are known because the distance the distance from parallax or whatever you call the trigonometric measurements which are close to that. So you take those specific variables and make a calibration. Now that you have done, as long as you detect these variables anywhere in the sky, you will be able to measure distance to different galaxies also. So the nearby galaxies, people see these variable stars, and then what you do is that you just keep measuring this and find out like how the intensity or flux of this star is varying as a function of time. You can take two minima or two maxima and calculate the period, and that period will immediately give the luminosity, right? And whatever flux you are measuring, flux means average flux. You can ask like when it is going up and down, which flux I will take. You can imagine like a steady state flux average over a larger time scale. Then you will be able to find the distance to these galaxies. Okay. Then we introduced another thing which is known as supernova. So what happens is that supernova are one of the end stages, and we talked about two kinds of supernova. One we said that it related to core collapse. So it means like a big star, when it collapses, because then suppose imagine that for some reason the nuclear burning is stopped, and even if I go to very high temperatures or higher densities, I am not going to create any new nuclear reaction because these are all heavy elements. Whatever I am going to create by fusion, they are not going to be stable. To reach that kind of state, this kind of bouncing, instead of collapsing star will bounce back and give you a supernova. That supernova will start as a bright flash and it will evolve afterwards. And this kind of thing you can think of a lot of variations in the sense that it is not necessary that the collapse can be perfectly symmetric or the bounce can be perfectly symmetric. So whenever you say, you can take this way, you can bring a cracker from the same manufacturer, 5 of them, and you place the bomb and blast them 5 different times. Whatever things which remains there, it will not be identical because these guys allow for asymmetry in your experiment. So that is the problem. So whenever you find supernova, the light will be there, but it need not be something like standard. All supernova will have same luminosity, all supernova will have some same property. This cannot be established. So this kind of supernova, these are typically called supernova 2, type 2. They are useful for information like when they blast, they do a lot of other things to the surrounding gas, which is very important for evolution of galaxies, but not for distribution. Whereas we talked about another set of these things. So you have a compact star, means like it is not a star in that sense, there is no nuclear reaction going on. This is like an extremely compact star, and it is held down to a particular shape because of degeneracy pressure versus gravity. Gravity tries to pull it to the center, and it is sort of opposed by the degeneracy pressure. So this is electron degeneracy. If it is there, you will call it as neutron SRE. Why to us? If you are in neutron degeneracy regime, you will call it as a pulsar or neutron star. Suppose if there is a big normal star which is going around, and if it puts some material into this, and if it material comes and falls with high speed, it can trigger nuclear reaction in the surface. Right? Surface nuclear reaction. And that's what I explained to you yesterday. This can, again, it will have a rise in the intensity. But we also said, now this nuclear reaction means that you are creating several sets of isotopes. And whatever isotopes you are going to create, it depends on the surface properties of the stars, that white dwarf or whatever. So there is and one thing we know, if I generate an isotope, the decay time of the isotope is fixed because this depends on what we call as energy levels, what we call as a decay time scale for that particular isotope. So you know that, so that means the way the light will dim in this supernova can be well predicted because the intensity of the light is mainly dominated by the decay of these isotopes. So that is the idea. That means people know if you find a supernova and if you find the rate at which it is decaying, you can calibrate it with the intrinsic power or luminosity of that supernova. So what you have to do is that you see the supernova, you don't know the absolute energy per unit time coming from this object, but you know how much energy per unit time you are receiving. This is what is called flux. You just plot flux as a function of time. The way it is decaying, it will tell you how bright intrinsically the object is. Every time you know how bright an object intrinsically, it means that you will be able to find the distance without any problem. So supernova, this is another standard candle. Because supernova are extremely bright, you can see them to any distance you want, right? So that is the biggest advantage compared to all other candidates which we talked about for measuring. Seafield variables are difficult to detect because these are first of all embedded in stars. Galaxy means all sorts of stars are emitting light. One part will be Seafield variable. You have to identify and say that these are variables I am interested in. It has to be very close so that you can at least see some results on stars. So what people have done is that you look at some galaxies where supernova goes off and also Cepheid variables are there. Since you have calibrated Cepheid variables with other techniques, now you can ask if I measure distances from supernova and measure the distance of the same object using Cepheid variables, do they match or not? Right? Ideally, if they match or if they don't match, I have to make some correction. If I calibrate relationship between these two, I am sure now that when I have only supernova available for my measurement, I will be comfortable saying that I am measuring the distances accurately. Okay, this is the point. So this is one of the examples of supernova calibrations. You can see like sort of these are distance calibrations are very good. This side is what is called a CZ. I will explain to you in some time. This is a proxy for y-axis is a proxy for distance. Will come in a few minutes. Okay, wait. And this one is a proxy for the luminosity. And you can clearly see if you look at the intrinsic luminosity versus whatever is the distances, you have nice calibration. One can use it. So this is an example of this side is based on supernova, it is based on Seafield variables, and this is the equality line, and you see that wherever you are able to measure the distances based on both the methods, you will be able to get supernova. So this is the point here. What you can do is that you will be able to measure distances to objects further and further and further and away, because don't worry about this axis because it will take 2 minutes to explain to you, so that will be interesting. So you find that the luminosity distance, you can measure distances up to very large, meaning you can measure accurate distances for objects which are placed at very large distances. So this is a summary. I mean, all these things are actually available in Wikipedia because the pictures I have taken are all available, but what I am saying may not be written in that way. Okay? That is the only thing. So you start with radar measurements between Sun and Venus. This is basically, you are talking about solar system measurements. This is more or less like the best way, the way we are measuring distance of an aeroplane which is coming to attack us. This is exactly what we are doing, right? That's the technique. So this is the physics technique which is well acceptable. Okay, from here you use parallax to nearby stars. So the distances you are covering is something like 10 to the -4 light year to radar techniques. Here you are going up to 100 light year, where you are actually using this parallax. And then main sequence thing, I explained to you main sequence, making the main sequence adjusting. You are going up to 10 to the 5 light year. That means within the galaxy, you can go to edges of the galaxy and also measure these distances. So then nearby galaxies, you are seeing Cepheid variables, you are going up to 10 to the 7 light years, because this actually, even though the calibration is done for Cepheid variables which are in our galaxy, actually we can detect Cepheid variables up to whatever 10 to the 7 light years, which means that you are comfortably detecting these objects in nearby galaxies and you are measuring distance to their nearby galaxies. Okay, so if you believe in white dwarf and supernova, I think these two things I have not explained to you, but it is not needed for our most of our purpose. Then you find that you can measure galaxies, that means you can distances to galaxies using supernova, and then you are going up to the distances of 10 to the 10 light year. Okay. So this means that you are almost going to the edge of the universe. If you have sensitive telescope, what you have to see is that when supernova goes up, they will become as bright as a typical galaxy itself for a brief period of time. So it is very easy to detect them at faraway distances, and one can then map them. So this is first part. But so you have any questions related to distances? Because I have to introduce some other things. Maybe I will do it in the next class tomorrow. But you have now idea how astronomers or cosmologists are measuring distances. Before I move on to mass estimations, the mass we will spend today, different physics will be used to measure masses at different distances. I will explain how it is done, and I hope you can follow that. But before doing that, there is a small amount of catch involved in whatever we are doing. So one is related to, when I talk of distances, you see, we are saying that here we measure distances of something like 10 to the minus 4 light year, which is meaning like, wow, this is much, much smaller. Time scale is not much. This is within our lifetime. It is not a big deal you are going to measure. But immediately you realize, even when we are talking about nearby stars, the distances are something like 100 light years. That means the photon you are receiving, they started from the star even before your father was born. Maybe your grandfather was born, depending upon how much their age is. Basically, the photon you receive today was emitted 100 years back, at least. That's the idea of 100 light years. So this brings us to a problem already. When we are doing any of these measurements, we are going to assume that nothing happened between that point and today. This is not that dangerous when you are talking about 100 years. You would say that we know sun has not changed in 100 years. Otherwise, our earth would have gone for a toss. Imagine sun's temperature changing by 10%. We will all die. So we cannot have constant increase of 10% temperature or decrease of 10% temperature from sun. It would have killed. So whatever people are talking about, sun is changing, this thing, that there are minor. Sun's magnetic field changing. It's not dramatic. Okay. So that's what we will say. Okay, 100 years, whatever we are seeing, star has not moved very much, it has not dimmed or whatever. So our distances are okay. Imagine star emits photon. Before that photon arrives at me, it has moved some distance. Then what am I measuring? Right? So we have to remember, every time we talk of distances, we are also into this dilemma. Whatever probe I am using to measure the distances, these lights have started some time back. When it becomes dramatic, is that when you are dealing with distances of 10 to the 5 years or 10 to the 7 years, when you are around 10 to the 7, 10 to the 8 years, you are talking about the age of the star itself. Some of the stars, like which you are seeing today, they may not be there at all. They might have gone out of your main sequence and gone somewhere else. So this is interesting for us. At smaller distances, you are worried about what happened to these objects. When you go to very large distances, for example, if you are talking about 10 to the 10 light years, we are telling this is the lifetime of our whole universe itself. Which means that by looking at objects which are further and further and further and away, we are actually seeing how things were long, long time back. Imagine that we are sensitive to seeing light coming from India 100 years back. We will not be wearing such dresses, right? We have seen photographs, people having khadi and this and that, and no Western outfit for common people. Nowadays, you would see people going in street with dhoti and some in this, right? So you can clearly see that is the kind of dramatic thing you will see. Exactly like this, if you go back and start seeing objects which are far away from each other with respect to us, you should see exactly how things have changed. So the fact that distances are enormous, fact that the speed of light is finite, which means that there is a time machine in front of you, you can actually see how we evolved starting from so-called Big Bang. So this is why this becomes extremely interesting. So the distance measurements, we have some ideas of how we are measuring, and we will go into some new units and all. This is why I didn't tell you. I was plotting some other calibrations. I'm not going to explain this plot in very detail, but you just imagine that we can go up to few gigaparsec where we can measure distances. A parsec is something like 3 into 10 to the 18 centimeters. A gigaparsec means 10 to the 6 times that. Right? So we can, sorry, megaparsec 10 to the 9 will be gigaparsec. Okay. So I hope that you have some idea of distance measurements. And now it is up to you to decide whether these measurements are accurate or not. Because that is the point you have to remember. And lot of things we are discussing, lot of debates one is going to make related to whether this is the universe you are going to live in, this is the model of the universe, or no, some other thing is the model of the universe. The validity of all these things depend on such observations where we are going to pin at different stages, different physical processes, and we are going to believe that this physical processes is what is exactly happening in these objects, because of which their intrinsic emission per unit time is. So now let's move on to measuring masses. Okay? How will you measure mass? Of course, we are not going to have a scale, or we are not going to have something to measure. So we have to use some simple technique. The simple technique one uses is excuse me, sir. Yeah, is there any question?
Yes, sir. How do we get the data? Suppose if we want to measure the Milky Way distance by using main sequence fitting.
Data means you have to go and observe with the telescope.
Data. I'm asking about data, sir.
Yeah, data is, that is the data, right? You observe and take a picture and look at, you plot individual stars, you measure color, individual star, you measure the fluxes.
Okay.
You have to generate these points. That is data, right? So data in astronomy comes from telescopes. Okay. So second thing, I will go slightly quickly because again, if you can measure distances to see, if you know distance of Earth from Sun, you can calculate mass of Sun from the period of Earth itself. If you know how much time it takes for Earth to go around, you can calculate mass of Sun. In fact, in this situation is very easy because mass of Sun is much higher than mass of Earth. You can treat Earth as a Earth as a test particle which is going around without any back reaction to the force itself. The simple way of measuring. So you can measure mass of Sun, and mass of Sun is how much? 2 into 10 to the 33 grams. These are the numbers you have to remember. If you know mass of Sun, it's also easy to remember luminosity of Sun, energy per unit time, is 2 but different units. If 2 into 10 to the 33 is mass, 4 into 10 to the 33 is x per second of the luminosity of Sun. So these are the numbers you remember, because when people tell you what is the luminosity of something, they will say that this is 5 times solar luminosity. Because solar luminosity becomes a unit, because the astronomy numbers you don't want to carry these big numbers, right? So you remember solar luminosity means 4 times 10 to the 33 x per second. Solar mass means 2 times 10 to the 33 x per second. So how it is calculated? Like this. And you can cross check by adding more and more. Of course, you know that we don't do it so blindly like circular orbit and all. You have to make the correction. You have to also feel that if I take a planet, if it goes around a star, nearby objects can perturb this orbit little. If you can measure this perturbation, then you can also detect planets. This is the way people have detected in the past Uranus and Neptune and all, because you see that minute deviations in the orbits can be computed. But if you want to measure mass, those things won't affect. Okay? Because the biggest bully there is Sun, and you will calculate. You understood? If you have two such stars going, a star of similar masses going around the center of mass, then you will not be able to measure individual masses, because it is not, unless otherwise you have a lot of information. So you can have this kind of coordinate called reduced coordinates R1 plus R2. R1 is distance of one of the guys, R2 is distance of the other guy. And if you define M as M1 plus M2, then based on Kepler's you can say P square by A cube is 1 over M. Where M now is, you can see like M is a mass, like this M1 plus M2, 1 by M1 plus M. So what you will be able to do in this system, you can treat as if things are going around the center of mass, then you can calculate this thing. So where this orbital periods or mass and radius you will get are related to the combined masses, right? You can get a combined masses if there are binary, okay, based on this measurement. Of course, people now know we have the centers of each galaxy. You have a supermassive black hole. This is another thing you will be introduced to. These black holes have masses of something like 10 to the power 4 pi solar mass. What does that mean? 10 to the power 7 solar mass means 10 to the 42 times 10 to the 40 x grams. Okay? So that is what you have to remember. So how do people know, for example, in our center of our Milky Way, how do people know there is a black hole? The way people have figured out is that you look at individual star, this curves. Suppose if you take this star and keep taking picture of this star over a year or so, this star will now move. Okay, and you can see that the star will close some kind of orbital motion. So you can now, if you can look at some 20-30 stars, you will find that all of them are moving in different directions with different ellipticity, but they are focused towards one point, because if you find that their motion can be governed by a mass concentrated in one location. So you know why this orbit need not be a circular orbit, right? Circular orbit is one of the solutions. The orbit will preserve both angular momentum and energy of the system. If you put a star in an orbit, it comes back to the same point, means that it preserves angular momentum and total energy. If you want to understand, this is the exercise people do now. You take a pendulum, you leave the pendulum here, it will go and come back to the same point only. And you will see that some dramatic things in the YouTube where person keep it in the neck and the ball goes and it doesn't come and hit that person because of conservation of energy. If it was not there, you know what happens. So exactly like this, depending upon what angular momentum and what total energy of the system, it can take different kind of orbit in the 3 dimension. It can go around circle. It can be a elliptical thing with the sun sitting at one of the foci, like that. Okay. So you can actually, by making the orbits, picture of these orbits. So it is a well constrained problem. You are looking at different objects moving at different speeds. You will be able to locate and say how much mass is concentrated in the central region. Again, till now, what we are using is that here you will use the distances. You have to have some idea of the distances. So this distance measurement has to come. We should have rough estimate of where is the center of our galaxy, how far it is. Then you know that what is the scale over which this motion is there. Because to measure mass, we should know the orbital parameters. So the distances will assume some of the things we are talking about. So we would have made this one. So you understand. So local value of masses, most of the time, masses are measured by using the effect of gravity only. So effect of gravity is two things. Effect of gravity is only one thing because it brings everything closer to the center. Okay. So we have already found one effect, which is the formation of star, where you push the gas closer to the center. Why it did fall? Why gravity did win in the end? In the case of gas, is that gas builds up pressure. What is the meaning of building up pressure? Building up pressure means density and temperatures goes up, right? That is how you build pressure, just by compression. And the pressure at some stage stands up and say like, no, I am not going to listen to you, right? So how much the gas can be heated depends on how much is the mass which is involved. If there is so much mass, it will overpower. See, pressure keeps building. The collapse will stop only when the pressure of the gas is somehow matching with the gravitational pull. So you can take a small layer and ask how much is the force due to pressure which is going outwards, how much is the force due to gravity going inwards. If they match, it will be there. So do you agree intuitively, if the mass is very high, the gas is involved, when I reach this equilibrium, means like I reach an equilibrium, no more I am going to collapse. What do you expect? The gas will be hotter when the mass is more. Do you agree with this? Because mass is more means I can keep compressing. The gas is same. You have to remember that. Same hydrogen atom. In one case, I can bring it very close so that the pressure can go up. Pressure going up means temperature goes up. If you think of some simple adiabatic situations without any. And this goes by the name, this relationship between gas temperature and gravitational potential in an equilibrium situation goes by the name virial. You would have heard something called virial theorem. So what is virial theorem? It connects between potential energy and kinetic energy. So what is that? So what does it mean? So if I have a potential, my kinetic energy will be half the potential energy. So there is, if you set up an equilibrium, exactly we are doing here in the case of gas collapsing under its own gravity, you can have a situation where the net kinetic energy can be decided by the underlying potential energy. Of course, you will see what happened to the other half of the potential energy that is usually radiated away till you reach there. So you will, this is called virial theorem for gravitating system. You will study at some stage when you do gravity. This also goes by the name scalar virial theorem. The implications of virial theorem is that if the gas is collapsing into a gravitating situation, temperature can be a proxy for underlying mass. For example, if I go and measure the temperature of the gas far away, I can measure temperature of the gas, then you will tell me, oh, you found the temperature. If this is in virial equilibrium, the mass has to be this. Right? So this is one way of measuring this. Of course, you can also think of a slightly different problem. See, this one, whatever I talked about it, everything is gas which is going into this. For example, I have a situation like a galaxy. What is galaxy? Or you can think of a situation like collection of stars, right? So it's like a star cluster. Again, the same thing will happen. When you have two objects, what is the idea of they going around the center of mass? The idea is that all motions are falling towards the center of mass. That's it. Gravity always tries to bring. You put two objects, it will try to bring them closer to the center of mass as much as possible. If I put n number of objects, all of them will go towards the center of mass. That is the definitive motion. If nothing happens, they will go to the center of mass. What prevents this particle from, or these stars from not going into the center of mass is what is known as angular momentum. This is exactly same. We have seen that angular momentum can act like pressure felt by gas, in the sense that if you put something go around your sea now, that bucket to put water, and even gravity cannot bring the water down because angular momentum, conservation of angular momentum will ensure that there is a force which goes that way, and that is sticking to that. The same thing you can think of. If I take a star, the center of mass will try to bring the star inwards. If the star has correct angular momentum, it will keep going. So, angular momentum, if you imagine that all stars have similar masses, angular momentum will be related to what? Angular momentum will be related to what kind of velocities they have. It's at a given distance, mass, distance, velocity. These are the things which are related to angular momentum. If I say that the stars are of similar masses, you can clearly figure out velocities of the stars will be proxy for angular momentum, how fast they are going around. So again, so you can do two things. One is that you can measure gas and measure temperature of the gas, or you can go and look at the velocity of stars in a given region. Ideally, you would like to see how they go around like the way we are showing here. In the galaxy, it is impossible. Typically, a star will go one round. It will take only 10 to the 8 years. Okay, it is 100th of the lifetime of the galaxy. So it is a short time as far as galaxy is concerned. For us, forget, because we will not be able to actually measure how the star is moving. That we will not be able to see. We will not be able to see the orbits. But we will say that, okay, let me look at locations. I go to a particular location. I am unable to resolve the stars. The light I am receiving from this galaxy is coming from collection of stars. Some stars are moving towards me. Some are moving away from me. Some are going this way. The star which is moving towards me will make all the spectral lines shift bluewards. The star which is moving away from me will make all the spectral lines shift redward. Star which is moving like this will have no shift. So that means the total thing I will see, if I take an absorption or emission line, it will be very broad. Okay, so it is like this, what we are saying. So just I will make a picture so that you will understand whatever I said. Suppose imagine this is the galaxy. I take a small patch here, patch of light. I look at the spectrum of light coming from there. So this spectrum, if I look at an absorption line, it will be something like this. This will have a finite width. So here I am plotting lambda, f lambda. It will have some finite width. It will not be a delta function, which you expect from a quantum mechanics, simple quantum mechanics. Even quantum mechanics will not give you a delta function. Because of uncertainty principle, you will have some width, which is called natural bandwidth. But you will find that this width will be now decided by the following. If this is consisting of several stars, some stars are moving towards us, some are moving away from us. If I take one star, the spectrum will be something. I will plot one star spectrum which is moving towards me. So it will be something like this. One star spectrum which is moving away from me will be something like this. Okay. But if I am looking at a collection of all of them, that means this absorption will go from 0 to minus v or 0 to plus v. That maximum velocity depends on what is the fastest star in that location. Rest of them will be weighted by what is the angle at which they are moving. If they are moving perpendicular to me, all of them will be 0. If they are moving like this, positive, negative, depending upon your choice. So when you look at width of this line, width of the line will tell you the dispersion of velocities in that particular region. How much is the spread? How much is the spread you see in the velocity of these objects? And this spread will be introduced by what? This spread will be introduced by motion of your stars around this galaxy itself, right? So again, you have to remember some simple principles you have understood. If I put a test particle here, if it is influenced by gravity and if it moves like this, what is the mass which is important for you? The mass which is important for me is mass inside that orbit of my interest. Mass inside that orbit is integral of light coming from all stars. So we can imagine that I can go and find velocities or dispersions or how it's for one star, right? If you imagine that n number of stars going in all directions, some is rotating like this, some are rotating like this, you will be able to find the width of the absorption line will give you what we call as dispersion. Okay? The dispersion can now be related to underlying potential and we can measure the masses. Okay? So much of theory, let's see how it is done in real life. The first thing we are doing is what is known as rotation curves of nearby galaxies. Use the same technique. You go here, imagine that this is a galaxy. You go to each point and imagine this galaxy is very special. So let's make a simple galaxy. So this is my galaxy which is edge on. So that means all particles are, and they are going to rotate like this. They are rotating. So imagine this is like this, it's rotating. And for you, it looks like an edge on thing. But actually, if you go from top, it will be a disk which is rotating like this. So in this case, since this is going inwards, if I take a small piece of section and look at any spectral line, what you will see, it will be red shifted away. Another thing will be blue shifted inwards. Okay. If I go here, so what I can do, what do you expect velocity of this type? Velocity at which the rotational velocity will be decided by mass inside that region. Correct? So as you go to different distances, the mass is going to change. Agree? So you will be, in principle, able to make a connection between how mass is distributed within a galaxy, and if you integrate that, you will get the total mass. Okay? So this is what is shown here. This is the galaxy. This is the galaxy. Okay, what people have done, they use what is known as H1 21 centimeter line. This is a hydrogen line, which you can detect using GMRT, for example. GMRT is built for detecting that 21 centimeter lines from hydrogen. So these are not stars. They can distribute up. They don't just confine to the regions where stars are there. They can go to very large distances. So what is done here? This is suppose you take this is the center. You go to different distances along the major axis. Okay, and calculate what is the velocity. Velocity you will measure through Doppler. You just plot what is the velocity as a function of distance. And what is shown as b is what is observed. Okay, so it is very interesting. What happens to the velocity is that if you go closer to the center, you find that velocity is sharply increasing. As you go outwards, velocity is sharply increasing. If you are beyond some level, you find that it remains nearly constant. Okay? So this is what one finds for typical galaxies, which means if you say that potential, so what exactly is that? So you can now go back to our standard equation. The equation governing this will be right. V square will go as Gm by R, correct? So I measure at any distance R will be like square root of this. Okay. And what is rho of R? Sorry, M of R? Integral of rho of R is kind of this. So these two things you understand. So if you think of a Kepler kind of problem, in Kepler problem what happens? Mass inside R is fixed. Because all masses are concentrated in the star, for example, in sun. So this is not going to change as a function of radius. So this is a constant, this is a constant. What happened to velocity? As you go to larger and larger distances, velocity will fall as 1 over square root of 1 over r. Correct? This is what Kepler said. If you go further, velocity should go down. So that part we understand. So clearly, what it tells us is that nowhere we have a situation where all mass is centered in a small region, right? We are not in a situation where all the mass is concentrated in a region, and when you go to further and further distances, we are actually looking at a centrally concentrated mass. If that has happened, you would have seen a curve like this. If this curve demonstrates that if the mass is concentrated only in the place where you see stars, what do you expect? You expect something like this. This you understand. Why? When mass becomes constant beyond some radius, this guy will come out and you have to go to this one. Okay, now you are clever people, you have to answer me various questions. When I go to the central region, what we are finding is that this is increasing. In fact, actually it increases like almost like linear. As you go to higher R, my V goes up. So how do I get it? So what we are saying here, I want V to go as R. How it is possible? How do I do that? So if I want that relationship, V square to go as R, V square should go as R or whatever, that linear relation, whatever I want to gain, here I should have something which is more than R square. Yeah, otherwise it will go as 1 over R, V square will go as 1 over R. If I want V square to go as R, this should become right, R square. Correct? Or if I want V to go as R, this should become R cube. So you clearly understand, depending upon what I want, I have to decide. So now let's say I don't want this V to depend on radius at all. Then what happens? These two should cancel. That means if I keep integrating mass for larger and larger distances, mass should go as R, right? That's what it is. So you can clearly see, if I take constant density, suppose if you say, to start with, if I take constant density, this guy will come out. So this integral will be R square dr. So it will go as R cube, right? Because integral, if I imagine constant density, Kepler equation or whatever gravitational equation is telling us, if the distribution of matter is constant density, if I go to larger and larger radius, correct? What happens to my mass? Mass increases R cube, that is, we know that 4 by 3 pi R cube into rho is the mass inside that thing. If I put R cube here, this whole term will become R. That means B of R will go as R. So if you find B of R going as R, what you conclude? You will conclude that in that region, more or less objects are distributed with constant density. Right? You agree with me? It's a very simple physics only. To understand why this is flat, if I want this to be flat, what do we say? We say that you make this guy. So to make this? I want it to be R. If I want integral of this quantity to be R, what should be this product? R square rho of R. It should be constant, right? So that is possible only when rho of R goes with 1 over R square. Right? Rho of R is proportional to 1 over R square. Suppose if you do that, if you assume that rho of R is proportional to 1 over R square, then you will find the velocity will remain constant irrespective of radius. So what do you understand? So what we understand now is that when you go and look at a nearby galaxy, you find the following. You are finding that, so this curve is known as the rotation curve. Rotation curve means you find the average velocity as a function of radius. Okay? This curve has a pattern. It increases in the beginning and remains flat. The increasing part you can understand as if in the central regions, it is almost like constant density matter. But as you go outside, the matter density falls as 1 over R square. So what is interesting for us here is that this 1 over R square fall is not seen in galaxy. If you look at galaxy light, if you ask where are the galaxies, typically galaxy means optical light that you see. Typically it's like this. If you take a galaxy, you will find these light emitting regions. But if you see where this hydrogen emitting regions or the hydrogen emission comes from, it typically comes from 3 times. So this is hydrogen. This is star. Okay. The important part. First thing is says that the gas is present everywhere. That is a good news. There are stars, there are also gas everywhere, and you will hear about this gas somewhere else. The most important point for us, what we are saying, when I go from here to here, I am finding density fall as 1 over R square. So their mass density, if it is contributed by star, the star should also show 1 over R square mass, but it's not there. You don't see that. That is the first point. That means this 1 over R square mass is contributed by something which we don't see. Second thing is that you can now integrate it, right? You are getting m of R. If you go up to this distance and integrate, you find that the mass you end up with, you can do 2 things. You look at the luminosity coming from star, total light per unit time coming from full galaxy. And you say that this is related, suppose you know that if there is a star like sun, how much energy it will emit. You know that 4 times 10 to the 33 x per second. You find out what is the total energy coming from this star. If you say 10 to the 43 x per second, so you can say, oh, okay, I need 10 to the power 10 solar mass of star forming gas so that it can produce this much luminosity. Now you can compare with this. See, one place you are doing physics of stars and how they emit light. Another place you can go and say, like, I look at the kinematics of the gas, and I am assuming the kinematics of the gas follow our Newton's law. That means there is an underlying gravity into which this material is rotating. If you do this, you estimate a mass which is much, much larger, sometimes 100 times more than what you see in light. This is what is called darkness. Okay? So the understanding of these large velocities requires you to have a gravitational potential set up by some objects which you don't see. Only thing you see is that you see the effect in the gravity, right? Gravitational influences. This is the picture one has to create. Of course, if you are still in 10th standard, 11th standard, 12th standard, you just believe because it is in the textbook. But if you are doing research, there are 2 options. One option is, yes, there is a dark matter which is present, because this dark matter is, you don't see it, and we have to believe that Kepler's law is valid. If Kepler's law is valid, for the rotation curve to be correct, I need density to fall as 1 over R square. I don't see it in gas, or I don't see it in star, so it has to be a dark matter. But You can also say, look, I am saying dark matter because I have put Newton's law. I know Newton's law is valid at the scale of planets, Newton's law is valid at the scale of something. But why should it be valid at the scale of, instead of force going as 1 over r square, potential going as 1 over r, if you make a change, r plus something, r minus something, you can then decide what is the force law you need so that you will produce this curve. Instead of changing the masses, you say that mass is correct. You are now going to introduce density dependence force laws. So this is what is known as modified Newtonian gravity dynamics. So there are two kinds of proposition to understand the rotation curves. One is the simplest thing. I think 99.9% believe that is dark matter. There are so many other reasons to believe why dark matter picture is correct. But there is a small, tiny little population of people who are extremely important for our scientific endeavor, because we need to have people questioning standard paradigm. Otherwise, you will never improve, because you will be going, it's like a frog inside the well. You will never be able to explore anything. So this is just, you should be aware that there is a different proposition. This is what is known as model. So you are with me till now, right? You understood rotation curves. You understood how we got it. So another way of estimating mass of star, I told you, you can look at the width of absorption lines. This width should be related to the distribution of velocities in that region. And again, you can connect this sigma, the dispersion, to mass inside that radius. One can calculate. So I will not go into the detail, but you understood the physics, basic physics behind how it is done. There are two more things I wanted to explain, and then we'll stop. Maybe we'll go to this one, then we'll come back. So now the question comes, how do you measure masses of clusters of galaxies? Suppose you say that now we have a problem. I asked you to measure the mass of the galaxy. We have come up with an idea. There are two ways we could have measured mass. One is that I take total light and say that it is contributed by stars. I measure number of stars and they say this is the mass. Then we found out though we miserably failed, right? Because we are finding that mass is somewhere else. The distribution is somewhere else. So I go to the next level. One is that you start with star. If group of stars are there, you get what you call galaxies, or star clusters and galaxies. But if you put group of galaxies, because gravity will not stop. If you form a galaxy here, another galaxy here, they will start attracting. They are good. They always have attraction. There is nothing, no repulsion. So they keep coming, right? So you can also find a situation where there is a larger gravity, which collects all of them, big galaxies into a smaller volume, and this goes by the name galaxy clusters. So now you can ask, what is the mass of galaxy cluster? Again, you are in trouble. You can find mass of individual galaxy and count the number of galaxy. Then you say that this is my mass, because I have 100 galaxy. I know mass of one galaxy. I multiply by 100. I have mass of the cluster. But is that the mass which is present? You will already think that no, it should not be, right? Suddenly you have problem either with the force law or you have dark matter at the galaxy scale. If I'm mixing galaxies, why not this dark matter also influence? So definitely there is going to be something. So how do we measure the mass of clusters? Again, you have to use the same technique. Here the technique used is that since mass of the cluster is much higher than mass of a galaxy, what happens? It compresses to larger, meaning it can compress gas or galaxies to larger densities. So the first realization is that all masses are not in stars. We already said this hydrogen gas is present, for example, in addition to stars. If such gases are present everywhere in galaxy, when you bring galaxy together, you are also bringing gas, and this gas gets compressed by the gravitational potential. And since the gravitational potential is very strong, because you are thinking of hundreds of galaxies in one region. Galaxy itself has 10 to the power 11 stars. So you can imagine what kind of masses you are talking. So this gas will be stripped, means it will be heated to very high temperature, it will become a plasma. If you have a high temperature plasma, what will it do? It will emit X-rays. Okay? So whenever you find clusters, if you take your X-ray telescope and turn it towards the cluster, you will start detecting X-rays. But what do we know? X-ray, how much energy coming from X-ray radiation how gas got this much energy. Somehow you created these ions, and these ions are now emitting, right? So you have to create this much. You can even think of these ions have some kinetic energy. I convert this kinetic energy into radiation. Where do I get this kinetic energy? I'm getting it from the underlying potential. So again, you can apply Miriam theorem here. You find out what is the temperature of the gas, and you given the temperature of the gas can be measured from the amount of X-ray radiation I'm receiving from the source. Once you measure the temperature, you can assign what is the average kinetic temperature of a particle. This you know. If I know degrees of freedom, energy, I can find out, I can assign these things properly. What is the kind of kinetic energy of the system? So what Wheeler theorem tells you, kinetic energy is built into the potential. So I can find out the underlying potential. If I know the potential, I can calculate the mass. Easy job. People calculate mass. Again, you know what is the answer. Mass you calculate this way through X-rays is much higher than simple mass you will integrate. Again, this proves this picture that you have dark matter. Here again, this producing this kind of X-rays will be very difficult by just changing Newtonian gravity. Right? Newtonian gravity can explain that whatever what you call rotation curve of a galaxy because force equation you are changing. Here you have to understand virialization, underlying potential. That is a bit difficult to explain by modified gravity. That's why people think that your dark matter is an important thing. Okay. So last bit, I wanted to two more slides and then we'll stop. The next thing you want to say is that what else these very massive structures can do. So one of the predictions of GR is the following: is that when you take the mass and put it somewhere, the space-time around that region will be affected by this mass itself. In fact, this statement itself is slightly wrong because space-time and mass cannot be segregated. Space-time structure is set up by the mass which is embedded in it itself. Other way of saying is that you can visualize if there is a smooth space-time and if there is a mass present, space-time will be warped around this. Okay, so you can imagine something like this. So I have a simple picture of a space-time. If I put an object here, it can have a dent, something like this. Instead of going something just for our visualization. What does it mean? What is the importance of space-time? If I shoot a photon, it will just go around the space. That's the idea, right? It will just time evolution. It will go as like follow the space-time. So what will happen if it's a bit like our glasses, right? We have glass. If you don't wear the glass, all the radiation is coming. That's it. I have that proportion of. I get the proportion of d omega of my lens only, right? My whatever eyelid subjects some d omega. Only that much light I receive. So when my eye power goes down, I am unable to detect. So what do I do? I put a glass. What the glass does, it increases my d omega because it collects. I would have collected only this much beam. It collects a bigger beam and convert it into smaller beam and hit into my eye. So if I modify the rays, if I make rays converge, it will be as if I am collecting much more area from the simple. So this is the simple idea. You would have seen the same thing when you guys are not used to it because in the past we used to have something called transparencies. We'll have some sheets in which we write and that will be displayed. If that sheet is not perfectly aligned, if there is slightly curved, you will see all sorts of caustics happening in this thing. The same thing you see in the street when oil is spilled. So any layer you create which distorts the radiation which is coming or radiation which is reflected from that surface, that is a problem. So basically, if you imagine that, so this is what it does. Basically, if nothing is there, the rays are all going like this. If I put a gravitating object here, this ray will go and maybe slightly modified. This ray will go and modified bigger. This ray will go and modified like this. Because the space-time is curved. So you enter, it's like you go and you enter into you are thinking that you are going in a straight line. But actually this guy is off, so you get diverted. So what actually happens whenever you look at objects in the sky, You are not going to get straight radiation if there is some object in between you and the background object. And this goes by the name gravitational lensing. This gravitational lensing is one of the predictions of GR. If you go close to a gravitating mass, the mass will behave like a lens. And one can show that most of the properties can be approximated by whatever you do geometrical optics. So the way we would have done geometrical optics, wavefronts converging, all can be done. So what does it mean is that if you now think there is a concentration of mass somewhere, and we can predict how the light should be bent around or whatever. I should not say light bending, no light bends. Light always travel in a straight line. Only thing is that you are what you call so-called straight line. It is like this. Now you travel in a balloon. You put a straight line, it will appear curved. That is so bending of light is not a correct thing. It's the distorted space-time. Distortion of the space-time is the correct thing. So you will see several distortions, and this is one of the pictures you can see. So this is a picture of a cluster which we have detected in X-ray and all. But you can see a lot of these galaxies are very peculiar. No? They are all stretched. What is interesting, without me telling, I say that take one of these guys, and one of these objects, and just assume it is a curved object. And you can say that if it is there, where is the center of curvature? You can do this, right? And what you can see, it's very interesting. The object in this side, the center of curvatures are all towards this. Object in this side, the center of curvatures are all towards this. So what do you conclude? This is not symmetric problem, right? Or it is symmetric problem. You have to answer. What do you think? I take here, curvature is towards this. I take something here, curvature is like that. So it looks like all the objects are stretched with respect to some center. What do we know now? These are not objects which are present at the same distance like this bright central galaxy which you are seeing. These are the objects which are present far away. You see, these objects there is an object here, there is a galaxy here. It is not modified by this stretching, because these are galaxies which are closer to us. The galaxies which are farther away from us get stretched by a cluster which is sitting here. So you can now do it very interestingly. So now there is an additional problem. If you measure lensing, if you measure this one, you can map the mass distribution in that region. Because you know GR, you can calculate what kind of distribution is needed so that if I start with a standard galaxy, it appears like curve. I can calculate, and that's a function of distance. I can measure mass from this. If you are lucky, the same region you measure it in X-rays, you can measure the mass, and you can figure out what happens. Sanjan, I'll take 5 minutes extra because I started. Okay, so now this once again, now you go back and ask. Of course, it is not a fairy tale. These masses don't match. This is one of the unsolved problems, or one of the interesting problems in cosmology, because we need problems. Otherwise, it is boring. Otherwise, it will become textbook. If there are no problems, you have nothing to do with research. So this is one of the problems. One has to figure out why physics-wise both are there, right? One is related to realization, another is related to GR. So there should be some additional fixing you have to do so that you can understand this problem. This is one of the open problems. But what is interesting, which is important for us, is that the mass one estimates from here end up being very large again. It cannot, you just find out mass of the gas which is emitting X-rays. You calculate mass of all the stars which are present there. Then you find the total mass you get. It's much less than the mass you need to produce the gravitational potential you are looking at. Again, this conclusion is you need dark matter. And why you are not seeing dark matter in a simple way? What is the difference between dark matter and gas? Dark matter, it doesn't interact with it, and dark matter has kind of only gravity. And in fact, it was puzzled for such a long time till people found this particular object. Okay, that is the last slide I will do today, and we'll stop. This is what is called bullet cluster. So what is bullet cluster? Bullet cluster, there are several things which are plotted here. I'll explain to you in a simple way. Bullet cluster is nothing but there are two clusters which are going through merger. See, we were talking about one cluster. There are two clusters which are going to merge with each other. Then what happens? All the stars in this cluster, all the galaxies in this cluster and this cluster will start interacting. All the gas which is emitting X-ray in this cluster, X-ray emitting gas in this cluster will interact. All the dark matter here and dark matter here will interact. So what people have done is that now we can look at these are X-ray emission. So what you conclude from the X-ray emission? X-ray emission doesn't look like a nice spherical thing or whatever. And now people can conclude saying that there is one thing which is moving in this way. It looks like what you see when your boat is going in water. Then you see this nice thing, waves coming up. And it clearly indicates that maybe this cluster is going through this way. Okay, so you have seen that this picture you will appreciate, right? There is X-ray, another X-ray. Even if you take like a ball, one guy is going through the other, and the low mass one, high mass one will not get disturbed. The low mass one will get stripped, but gas will be stripped based on what is the velocity. And you are seeing that. This picture is okay. Now you want to know what happened to the darkness. So what people do now, you do this lensing measurement. You make a deep image, look at all the background sources and see which direction they are curved. And you go and measure the masses of, measure the potential which is required to do this. Okay? So what is that one? That one is this one. These contours which you are seeing are the measurements of dark matter. So how do you understand this? So the simple way you are understanding, after you listen to my explanation, you will understand what we are thinking first. Imagine that two clusters are there, two dark matter things are there. They don't interact with each other. What will happen? They don't see each other, they just go. Okay? So the lensing is the most massive objects, because more the mass, the bending will, whatever, the distortions of the space-time will be more. So when you look at distortions in the lensing measurement, they just probe dark matter, because dark matter has the maximum mass, more than 10 times mass of what you have. So if two of them pass through like this, it would have happened. So it's like some free going things go through like this. Suppose you send some small particles, it goes. When big guys want to go, what happens? We start hitting against each other. A big person or small person can be related in terms of interaction cross sections. If the same two things come, till they touch, they will preserve the independence. Dark matter will just go like this. Gas from this side and gas from that side cannot move freely like that, because gas will start interacting. This interaction will slow down. So that's what you are seeing. Even though you see the gas is moving in the same direction, it has not caught up with the dark matter. If this was individual, center of dark matter mass, center of baryonic mass will be same. So this measurement was the proof saying that there are dark matter in individual galaxies, and when they merge with in individual clusters, when they merge with each other, the segregation of dark matter and baryons will happen, because baryons will interact with each other. They will not freely pass through each other. They will in fact go like this and they will settle into one object easily. Whereas the dark matter thing will not see, just goes as if nothing is there. Only thing it will see is the overall gravitational potential. So it will not go like this. At some stage it will come back, because they will behave as if two objects which are just oscillating around the center of mass. So this is the bullet cluster experiment which proves. So I think now I will explain to you how to measure masses, how to measure distances, and these are the basic elements. And tomorrow probably I will introduce some basic ideas of objects and whatever we see in this class. I'll stop here. Anyway, just to save time, let's go for tea break, and any question you have, you can ask there. People who are in the hall, you can ask me tomorrow morning. I'll come 5 minutes earlier, so that if you have any question today, you can ask me.
लिखा नहीं अब थोड़ी देर
So I think I'll answer questions tomorrow. You are taking a break now. Hey, Saturday.